Alright, here we are again. More of me talking about astronomy. Lecture 5, maybe? We're going to be talking mostly about the big planets in the outer solar system, and then some stuff about the rings that all those planets have, and a bit about some of their moons. Here we go. So these are the 4 planets in the outer solar system. We got Jupiter, Saturn, Neptune, and Uranus, and they're real big. Jupiter is the largest planet, as probably mentioned a couple of times. It's something like 10 Earth diameters, so you can fit 10 Earths along the equator of Jupiter. Saturn, pretty big as well, a bit smaller than Jupiter, and Neptune and Uranus, both a bit smaller and similar sizes actually. Generally speaking, when we talk about these planets, they're the giant planets, but we differentiate them between the gas giants, the things that are largely more made up of gas, and then the ice giants. Remember, not just water ice. We say ices is also ammonia, methane, probably like ethane, and like other kinds of molecules with hydrogen in them. So Jupiter and Saturn are the gas giants. The other 2 are the ice giants. All of them, their atmospheres and a lot of their volume is made up of hydrogen, actually. Interesting thing to note too is that Jupiter is about 10 times the size of the Earth in terms of diameter. The Sun then is about 10 times the size of Jupiter, so 10 Jupiters across, meaning the Sun's about 100 times width-wise the size of the Earth. Just to look at some of the numbers here, yeah, in general, the outer planets are just much larger than the inner planets. And remember, when we talked about the formation of the solar system, a lot of the gas, particularly hydrogen and helium, that was around in the early solar system started to sort of get blown away from the sun once it was gone nuclear, and that's why a lot of these outer planets have a lot of gas, because that's where a lot of the gas that was around early on kind of got pushed out there, and that gets picked up by these planets that are in the outer solar system. So remember again, we talk about distances in our solar system, often use the astronomical unit, where the Earth is 1 unit away from the sun. Then Jupiter is a little more than 5, Saturn is almost 10, Uranus is like almost 20, Neptune is 30. Like if you look at, there's a difference between Neptune and Jupiter. Neptune is very far out in the solar system compared to Jupiter. And their period, again, in like years, how many Earth years that is, and it just gets longer and longer the further out you get, going along with one of Kepler's laws. And remember those, how massive they are. Jupiter's the biggest, it's the most massive. Funnily enough, though, it has one of the, I think, the shortest rotation in the solar system. It spins very quickly. It only takes about 10 hours for it to rotate around. Density-wise, most of the outer planets are pretty similar. Saturn, it turns out, is significantly less dense. About half the density of Jupiter or Uranus. And just in terms of the stuff that those planets are made up of, mostly hydrogen and helium. Also some other ices, right? Hydrogen and other things, like water, methane, ammonia, and a bit of rock, silicon, iron, magnesium, these are like silicates. The outer planets, though they're mostly made up, their volume is mostly made up of like gas and also kind of weird phases of gas and liquid. They do have cores, right? They still do have, we think at least they have rocky cores. It's just that those cores, like I said earlier, when the gas sort of blew out from the inner solar system, it started collecting around those cores, and so you have a similar like rocky core, but then you have a bunch of gas that accrued around it. And the pressure of all that gas pushing it on itself can do some strange things. And then one other thing I'll point out is that when we were talking about the inner solar system, you know, we've sent probes and things to planets in the inner solar system, to Mercury, to Venus, to Mars. We sent probes to all of them. They're all within 1 AU of the sun, and 1 AU of us too, because they're within that distance. It takes, on the scale of like months, for us to send something to them. When we're talking about the outer planets though, like Jupiter, it can take like years for us to get something to Jupiter. And when you get out to like Uranus and Neptune, that can take decades to get out to. Very far away. Sorry, one other thing I want to point out here also is having to do with the period, right? How long it takes for the planet to go all the way around the sun. Some of them is quite long. right? 85 years, or 84 years, 165 years. And we'll talk about it briefly, but hopefully you know that the reason that the Earth has seasons is partly because it's revolving around the sun and the orientation that it has towards the sun as it goes around. So these other planets also, some of them have seasons because they're kind of tilted and they're going around the sun, but it's pretty hard to study their seasonal change when it takes, 160 years for Neptune to go around. For one difficulty in studying the outer planets are the changes that go through as they revolve around the sun. This is a little bit about the appearance, like what we see when we look at these planets, and thinking a little bit even more in depth of like, you go below that, you go into their atmospheres a little bit. What is there? For the gas giants, the upper atmosphere seems to mostly be ammonia crystals, and so not even just gas, but they're crystallized pieces. So in a very similar way, the clouds on Earth, the clouds that we see, are actually mostly water crystals, right? It's H2O that's in the atmosphere, and it gets cold enough to start to condense and to form crystals, form solids, right? So our clouds are made up of water ice. Jupiter and Saturn, mostly ammonia ice. The ice giants, it turns out their upper atmosphere is mostly methane. And we don't have to go too deep into these graphs, but just kind of looking maybe at the different sorts of things that show up as you go deeper into the planet. And Jupiter, there's that ammonia, the ammonia clouds below that. I'm not even sure what NH4S, nitrogen, hydrogen sulfide, I don't know. But there's also water, there's H2O, there are regular clouds like we have on Earth too. They're just buried pretty deep in the atmosphere. So we don't really see them from looking down. All these clouds are above. Similarly, in Saturn, you do get to normalish sort of H2O clouds like we would be used to form in Saturn as well, but again, they're very far down. We don't see them looking in, or just looking with our eyes. You need to probe in other ways. For Uranus and Neptune, it doesn't really seem like they have any or enough H2O to really form clouds like that. It seems more like methane clouds, and then I think H2S is probably hydrogen sulfide, nasty clouds, if you want to go through those. Probably would want to go through the other ones, most of the other ones either. So if you look at Jupiter and Saturn, right, the upper clouds, the highest cloud level in Jupiter is about 100 kilometers above where it would be in Saturn. And so this is partly why when we look at Jupiter, we're actually seeing a lot of these clouds, like the ammonia clouds. We can see them directly. But in Saturn, those clouds form a bit lower, and there's other sort of ambient gas. I'm not sure what phosphorus, hydrogen phosphorus, or P2H4, right? There's sort of other stuff, not clouds, but just like gas that is around still. And so if we look down on Saturn, we're looking through a lot more stuff before we see actual crystalline clouds form, right? These ammonia clouds. So that's why when we look at Saturn, we don't see a lot of interesting features, right? It looks kind of bland. It's mostly like a beige-ish colors. Versus Jupiter, it's a lot easier for us to see these different clouds, so it has a lot more interesting color things going on. So as I mentioned, planets orbit around the sun, and a lot of them orbit in such a way where their rotation, or the way they revolve around their axis, is not directly in line with the way they go around the sun. Meaning that their axes of rotations are tilted a little bit from this plane that they're orbiting the sun. If we look at some of the planets, Earth, if you didn't know, our axial tilt, or the tilt we are away from that orbital plane, is about 23 degrees. Mars actually is pretty similar, 25 degrees. Venus is almost 180 degrees, meaning it's almost flipped over, and that's an indication, or that's also another way of saying that it's orbiting, or it's revolving in the opposite direction as the other planets. Right? So if we're all going this way, and you flip it all the way over, then it's revolving in the opposite direction. Jupiter has a very small tilt. Saturn, actually fairly similar to Earth and Mars, 27. Neptune, also pretty similar, a little bit more, but 28. Uranus is an interesting one because 98 degrees, meaning it's tipped over more than 90 degrees. It's like on its side. So it's revolving sort of like this as it goes around the sun. And because we have this tilt to our axis, that's how we get seasons. That's how we get summer and winter. Or the easiest thing is to think about the extremes of summer and winter, right? The reason that we have summer and winter is because at some point in the year, due to our tilt in our axis, the northern hemisphere is pointing towards the sun more, right? So more of the sun's light is hitting it, and it gets warmer. It's generally warmer. So in the picture up there, that's on the far left, at June 21st, the summer solstice. The northern hemisphere is pointing as much towards the sun as it's going to be, right? Meaning the southern hemisphere is pointing away, it doesn't get as much of the sunlight, it's colder in general, right? So that's winter for the southern hemisphere. You go all the way around, now the northern hemisphere is facing away from the sun, right? So it gets less light overall, which means it's generally colder, it's winter. And now the southern hemisphere is facing towards the sun, getting more light, that's its summer. And then in between you got the fall and spring. So if a planet has a tilt, a significant tilt, then it's going to have seasons, right? Because at some point of its orbit, of its year, going around the sun, one part of it's going to be pointing towards the sun more than the other. And it's just interesting to think about Uranus being that it's orbiting, or it's revolving on its side almost. The seasons that it has is very strange. Strange, or maybe just extreme. But yeah, if you think about, just sitting on the south pole of Uranus, then at some point you're always facing away from the sun, right? So if we look at that orbit, position 3 is where the south pole is facing away from the sun, and for most of that part of the year, the south pole is getting almost no sunlight. So you have very extended and extreme sort of winter, whereas the north pole is facing directly towards the sun, and so at position 3, the north pole is getting all of that sunlight, and it's the warmest it's going to be. And then you kind of go around to position 4, get somewhere in between, so north and south are getting a bit of light, go all the way back around to position 1, now the south is facing directly towards the sun, and you're constantly getting sunlight on the south pole. There's no normal night and day. You basically just have a very long day that's half the year, and then a very long night that's the other half of the year. At least if you're on the north or the south pole. If you're on the equator, you get a couple more 90 days. Also, like Earth, all of the outer planets have magnetic fields that are generated in their interior. Jupiter's is quite strong. It's something like 100 times the Earth's magnetic field, or the strength of the Earth's magnetic field. Saturn and Uranus is about 75% of the Earth's magnetic field, so a little bit weaker than Earth. Neptune is about half the Earth's magnetic field. They all do have magnetic fields, which tells you something that, our magnetic field is generated by hot material in the core that's revolving around. If you recall, I told you that really, really hot material ends up sort of pulling electrons from atoms, and so you end up with overall this charged material, this electrically charged material. And when that charged material moves around, when electric charge is in motion, that's how you create magnetic fields. So for the Earth to have a magnetic field, we have this really hot stuff that's all charged on the inside of the Earth that's revolving around. For these other planets to have that, it seems like they have to have some sort of hot cores like we do. They're revolving around. How do we know about these magnetic fields? Well, there's a number of ways. One is by looking at a particular kind of radiation, which is known as synchrotron radiation. And that comes about when charged particles like electrons and protons are accelerated or just kind of move through magnetic fields. Just like the Earth has electrically charged stuff that's coming from the sun at it, and our magnetic field protects us from, that solar wind that's leaving the sun is also eventually reaching Jupiter, and so it's getting this electrically charged stuff like electrons and protons. Its magnetic field also deflects them, and by deflecting them, accelerate them, move them around to their poles, that generates what we call synchrotron radiation. It's just a particular kind of electromagnetic radiation. So if we look at that particular part of the spectrum, then this is a picture that was taken of Jupiter's magnetic field, or magnetosphere. It's pretty large, right? As is indicated there, the planet is only the size of like a green oval, so the middle-ish sort of piece, and the magnetosphere extends at least twice that diameter, 3 times that diameter. And this is not visible light. There's no actual color there that you would see. These are what you call false color image, where, again, we use color to indicate often the intensity of things that we're looking at. So the magnetic field is very strong in that middle area where the color is really bright and I think white, and it gets less to the green and then very less to the red. Something that's useful here to extend to broader areas of astronomy is we found that when we look at the magnetic field of Jupiter, it has similar ways of acting, or it's similar in ways to other objects that we see when we look out into the universe. And it's similar, but it's kind of like a milder version. And those things, which we'll talk about later, are like dead stars and also like quasars. More on all that stuff later. Just to say that the way Jupiter's magnetic field acts seems to be pretty similar and just kind of a toned down version of those things. So it's a really useful thing to study because it lets us kind of extrapolate to understand those things better. These sort of ice cream cone looking things are like cutaways from each of the planets. Right? So we're just kind of like looking at this cone cut out of each of the planets. On the far left is Jupiter, right? You have that core, rock, ice, and above that is all hydrogen. Two different sort of forms of hydrogen. I'll talk more about that in a second. You look at Saturn, sort of similar in ways, rock, ice, then all hydrogen. Still two different forms. Uranus and Neptune, much smaller, and same sorts of things, except for they don't have that other form of hydrogen, this metallic hydrogen. So what is that other form of hydrogen? It's rather strange, but if you have a gas of hydrogen, and it's very cold, but it's under a tremendous amount of pressure, that metallic hydrogen, both of those areas in Saturn and Jupiter, metallic hydrogen, are underneath the outer volume of the planet that's just regular hydrogen. Molecular hydrogen, it's just hydrogen atoms. So there's this big kind of area of just regular hydrogen, and tremendous amount of it, and it's all crushing down on the stuff inside. So as you go into the planet, the pressure is getting greater and greater and greater and greater, and it grows so much that that gas gets pressed together and wants to sort of form into a liquid. But the fact that the pressure is like so tremendous, and it's not like just that the thing is cooling down in order to condense to a liquid, this weird other thing happens where you get hydrogen that's acting sort of like a liquid, but it's also acting sort of like a metal, which basically just means it's very conductive, like electricity will flow through it very easily. So you get this weird sort of liquidy form of hydrogen that acts like a conductor, electrical conductor. And that's what we call metallic hydrogen. The pressures in Jupiter and Saturn are great enough that they're able to create this form of hydrogen. The ice giants, though, neither of them are large enough to have that, or neither of them are large enough to get to those conditions where you can actually form that metallic hydrogen. So they just got the regular old molecular hydrogen. Another interesting thing about these giant planets is they have pretty extreme winds. On Earth, at least, the wind that we get is from a number of different things. It's from hot air rising, cool air falling, and then kind of making room for each other. Also partly from the gravitational pull of the moon and the sun on our atmosphere. Very broad strokes. But the thing is, we have surface, we have a crust, we have a hard surface. So when winds start moving on planet Earth, they're moving over that surface, and you can think about it as like a bit of a friction. Like you're trying to push a crate along the floor, you experience some friction that wants to kind of stop you or slow down that movement. On the giant planets, though, there is this huge range of the planet that there's no hard surface, right? You got to go really far inside until you reach any sort of hard surface. So that means that the winds that are generated by the same kinds of things, by convection, by hot air rising, cool air falling, by gravitational pull of the different objects around it, sun, they still generate all the wind, but there's nothing to really slow that wind down. So you get to some incredible wind speeds regularly on these planets. Like Saturn, near its equator, 300 meters per second, which I put down here, 100 meters per second is about 220 miles per hour. So right at like the peak is like 3, 4, actually 500 meters per second, meaning over 1,000 miles per hour. Right? Winds over 1,000 miles per hour around the equator at Saturn. And you can see in Jupiter and Saturn, it kind of peters out or gets a bit less as you move away from the equator. But on these planets, you generally just have this sort of like continuing wind storm or wind gusts that are just moving around the planet. Uranus, it's actually the highest winds are in between the equator and the poles. In Neptune, the greatest is around the equator, but there's also significant winds up near the poles too, and they're actually flowing in opposite directions. And so in Neptune, the wind around the equator is going one direction in general, and the wind around or between the equator and the poles is going the other direction. But in general, very fast winds. Finally, just a couple more tidbits. One interesting thing is that when we look out at other solar systems, other planetary systems, it seems like planets that are the size of like Neptune and Uranus, like the ice giants of the far reaches of our solar system, that size of planet is actually fairly common, at least in our galaxy. I doubt we've seen planets in other galaxies. Also, planets in between the size of Neptune and Earth, and so great planets larger than Earth and up to around that size of Uranus and Neptune, fairly common. Which is kind of interesting because our solar system doesn't have any of those. Right? We got Neptune, or we got Earth, and then Neptune and Uranus. Right? We don't have anything in between. Then again, we only have 8 planets. It's not a very large sample size. So there you go. Oh yeah, and as I mentioned before, the diameter of Earth is to Jupiter's diameter as Jupiter's diameter is to the Sun. You may have seen at some point before this thing called that we call the giant red spot on Jupiter, which turns out to be this enormous storm that's been raging on Jupiter for at least 300 years. You know, Earth could fit inside of that storm and still be plenty of room. It's interesting to note too that the storms we have on Earth, the center of the storms is we call like the eye of the storm. And if you've ever seen a movie or something where they go into the eye of the storm, it's very calm. Reason being that it's an area of low pressure. Right? Storms on Earth generally form around areas of low pressure, particularly like hurricanes, typhoons, that kind of thing. On Jupiter, it seems like in the red spot is an area of high pressure. So it's kind of the opposite. It's a little strange. Last thing, I just wanted to throw this image on here too, which is another very famous image, I believe dubbed the pale blue dot. And so it's an image that, one of our spacecraft took. Maybe it was Voyager, one of the Voyagers. But as it was passing Saturn, it sort of turned around and looked back towards Earth and snapped this picture. Near Saturn, it's an enormous planet, and you look all the way back, Earth is this tiny little dot. I don't know what else I want to say about that. I just think it's interesting to try to keep perspective as we go out. Now we're going to move on to talking about some moons, particularly moons in the outer solar system. On this picture, though, we still see our moon, Earth. We got one moon. We'll mention it, or I'll mention it later on. Mars actually has some moons, but they're pretty insignificant. They're pretty small things. Probably captured asteroids. Which is also moons of other planets seem to be a decent amount of them are asteroids that were captured at some point. But other ones seem sort of more moonish, or what you might think of more of as a moon, big round thing. And it turns out there's a lot of moons in the outer solar system. There's over 200 moons out there. Jupiter has quite a lot. I think I mentioned that before. It has at least 67. The moons shown there are the 4 largest moons of Jupiter. They're called the Galilean moons because when Galileo was using his telescope to look out at the universe, he spotted these 4 moons of Jupiter. Saturn, at least 62 moons. Uranus, at least 27. Neptune, 13. I think the sizes of these are relatively correct. So Jupiter, the 4 largest are pretty large. Saturn only has 1 very large moon, Titan. Uranus, none of them are all that large. And Neptune has 1 that's decent size, it's Triton. Astronomers at least used to think, before we were able to study these moons very well, that maybe they were mostly like the Earth's moon. And the Earth's moon, it's great for us. For the tides, we wouldn't be around probably without the tides. But it's not very interesting like on an active scale. It doesn't have active geology. I mean, it's kind of a dead sort of body that's just revolving around us. As it turns out, a number of the other moons in the outer solar system are much more active. Some of them, it turns out, that we're probably the most likely places that we could find life outside of our own planet. Overall, it seems like about a third of the moons in these outer planets have what we would consider regular orbits. and the other ones are irregular. So by regular, I mean it revolves west to east, just like almost all the planets do, except for Venus. They have low eccentricity. Right? Remember, eccentricity was like how squished is their orbit, so low eccentricity is like pretty circular. So again, like the planets revolve around the sun, most of them are pretty circular, low eccentricity. So most of the moons, or those regular orbits at least, are fairly circular. And regular also meaning that they're in the plane of the solar system. So that same imaginary sort of disk plane that the planets are orbiting around, about a third of the moons are orbiting in that same sort of plane around their planets. I think we're going to talk mostly about Jupiter's moons, so I could put down a little bit here about the other moons that are of interest or have interesting things going on. Saturn's moon Titan seems to be the only moon that has a substantial atmosphere and liquid hydrocarbons on its surface. So it actually has like almost like lakes and oceans, but they're not water. They're like methane and ethane. Enceladus, the little one, has active geysers that shoot out of it regularly. And it seems to be water that's shooting out. Neptune's moon Triton has a very thin atmosphere, has a little bit of an atmosphere, and is volcanically active. There's a substantial amount of volcanic eruptions that happen on Triton. One thing I forgot to mention is the moons that we would say are regular orbits, so they have regular orbits. From our understanding or from the way we've modeled things, it seems like those make a lot more sense to have formed with the planet, like around the time of the solar system forming, sort of like our moon. You know, Earth was still kind of in its formation when we think that protoplanet Theia hit and broke off some of the crust and the mantle and ended up forming the moon. It seems like regular orbits are probably something similar to that, or at least they formed with the planets. Whereas the irregular orbits seem much more like objects that were captured or like fell into an orbit of those planets later on. Here you go. The Galilean moons, right? Jupiter's largest moons. Just do a little bit broad sort of comparison, look at some of the numbers, and on this table we actually have the moon, our moon, and Titan, which is Saturn's moon. Just kind of pure comparison. Diameter-wise, it looks like Callisto and Ganymede are both larger than our moon. Not like crazy larger. Ganymede is 1.5 times the size maybe. Europa and Io are around the size of our moon. One's a little bit bigger, one's a little smaller. Titan, in comparison, is pretty large, right? It's around the size of Ganymede. We have then like their mass as compared to the mass of our moon. Right? Ganymede's about twice the mass of our moon. Densities, our moon in comparison is fairly dense. I guess overall the outer moons are lower in density. The inner moons seem to be greater. Down here there's a little depiction of the orbits of these moons. So it goes Callisto on the far outside, Ganymede, Europa, and Io. So it's like furthest out, next in, and closest. Reflectivity is just a measure of how much sunlight or light that hits the moon is bounced back. So our moon, not very much, 12%. Still a decent amount though, you know. That's partly why in the night, when the moon's out and it's not shadowed by the Earth, it can be pretty bright. But in comparison to these other ones, not all that reflective, right? Like if we had a moon like Europa around us that's 70% reflective, right? The night sky with the moon that's 70% reflective would be much brighter. Might be kind of annoying actually. Yeah, and also sort of a trend that looks like the closer you get into the planet, into Jupiter, the more reflective these moons are. So we're going to look at each of these a little bit more in detail and work our way in towards Jupiter. So look at Callisto first. So Callisto is very cratered, kind of looks a little bit like our moon, maybe even more cratered. If you look at the surface, there's a pretty large difference in the brightness of areas. Some areas are pretty dark, other areas are quite bright, and that seems to be because there's ice that forms on this moon, and again, not necessarily water ice, but ices in general are pretty reflective. So when you get ice forming on places on Callisto, it looks a lot brighter. And if you look up really close, well, really close, you know, a few kilometer scale still, then there's all these little like peaks like mountains and such that form fairly large, like hills, maybe not necessarily what you call like mountains, but pretty large things, right? I think it says the spires are 80 to 100 meters tall, they're 300 feet high, and ice tends to form on the peaks of them, so you get these bright areas. Like our moon, Callisto is tidally locked to Jupiter, so the same side of Callisto is always facing Jupiter, just like the same side of our moon is always facing the Earth. I think I've explained this before, but that happens when the period of the moon revolving on its axis is the same as the period of it revolving around the planet. So it's going around in the same kind of rate as it's revolving on its axis, and so that same side is always facing the planet. Temperature, highs of minus 400 degrees Fahrenheit, pretty darn cold. It's roughly the size of Mercury, but only about a third of Mercury's mass. Remember, Mercury was a high metal content planet. Callisto, definitely a lot less metal, and less rock overall, or ices. And as I mentioned before, we can probe the interior planets by their gravitational pull on each other, but also on spacecraft that we send by them. It almost like you're feeling out like how much is pulling in particular ways. And by feeling that out, we can kind of get an idea of the density and the distribution of stuff inside the planet. So from those kinds of probes, it seems that Callisto is not a differentiated body, meaning that it never got hot enough for all of the heavier stuff to fall in the middle and then get lighter and lighter as you go out. It's going to just spread all the way through. And along those lines too, it doesn't seem like there's any sort of interior activity going on this planet, or on this moon, which is sort of unusual for an object this size. It might have something to do with the fact that there's a lot of other stuff going on in Jupiter and it's pretty far out. But yeah, it's a little bit odd. Alright, so working our way in, Ganymede is the largest moon in the solar system. And there's a picture of it. I believe the colors are enhanced in that picture to really bring out some of the differences in the geography. Most of these moons are kind of like grayish if you look at them. Oh yeah, so it says here, darker areas are kind of the older, more smoother areas on the moon. Lighter areas seem to be a bit younger, where there's been more recent geological activity. So unlike Callisto, Ganymede does seem to have interior forces going on. So there's activity going on inside of the moon, which causes activity like volcanic activity, tectonic activity. And we can kind of see that in this close-up here, where on the bottom left of that close-up image in B is a big crater, right? So some asteroid, something came in and hit the moon at some point, but since then, there's been movement of the crust, the outer part of that planet, in such a way that it forced apart or created this kind of crack that runs through that crater now. So it's good evidence that at least since that impact, there's been some kind of geological activity. This body does seem to have differentiated, meaning it's got a core that's mostly rock, and that core is about the size of our moon. Ganymede's significantly larger than our moon. So its core is about the size of our moon. It has a mantle, and then it has a crust that's like mostly made of ices. Going back to the interior of Ganymede, what's going on inside, well, it certainly seems like there is heat being produced in there, whether it's kind of left over from its formation, which there probably is some of that. There also seems to be a process where the innards of the planet are being like squished and kneaded, like you would knead bread, by the gravitational pull of Jupiter. This is something we call tidal heating, or also maybe just said tidal forces at some point. We'll say more about this sort of tidal heating in the next slide. Right? But the fact that there is that heat coming out, means it's kind of a hot core, also means that it has this like tectonic activity, volcanic activity, and possibly even like plate tectonics, like the Earth. Not really clear yet, maybe. And we know that it has a magnetic field, which I think back when I was talking about the magnetic field of the other planets, it's a good sign that there's internal heating going on. We're going to think a little bit more about this tidal heating and why gravitational sort of pull could end up heating up something. Well, let's start on the upper left there. We're going to think about Jupiter as the planet, and then Ganymede is this body, the moon, that's orbiting around. So as the moon orbits a planet, its orientation relative to the planet keeps changing. Well, as long as it's not tidally locked then there's sort of different parts of the planet that are facing the moon at different times. Right? The moon's orientation to the planet is changing around, meaning that the gravitational pull on the moon is always sort of adjusting or pulling in a slightly different way as the moon goes around. Right? So at one point, the moon's being pulled gravitationally to the planet, and that ends up sort of scrunching the planet a little bit, squeezing it down a little bit towards the planet, towards like Jupiter there. And then as the moon rotates around the planet, now there's like a different sort of face of the moon towards the planet, and so it's getting squished in a slightly different way, right? Or along a slightly different kind of axis. And the overall sort of effect is as the moon goes around, it's getting like squished at all these different angles, and you sort of end up like squeezing and like kneading the moon overall, right? That's the tidal sort of forces squish it down, and then another point it's squished the other way, and the other point squished the other way. And you don't really need to do a lot of this contraction because we're talking about squishing down a solid. And if you squish down a solid even a little bit, you're adding a lot of heat, a lot of energy to that thing. And so by kind of squishing and kneading the moons, Jupiter is adding a lot of heat to the interior of these moons. That's what we call the tidal heating. And just a nice little gif there of kneading dough, if you don't know what kneading looks like. This idea of compressing something and heating it up is very useful, and just a general property of atoms and like gases, liquid and solid. If you compress them, then generally you increase their temperature, heat them up. If you don't know, then the normal combustion engine, like normal gasoline engine, has spark plugs. And inside that engine, there's mixing the gasoline with air and compressing it, but also having this little spark, right, that ignites that gas and air mixture and pushes down the piston. Right? And so that's where you get this up and down motion going that's translated into this turning motion, and you can turn wheels. In a diesel engine, or a lot of diesel engines at least, they don't need a spark plug. It's actually the compression that leads to ignition. So you have that diesel fuel that's in the piston, or that's in that cylinder, and you really compress that fuel. And so it increases its temperature greatly, it adds a lot of energy, increase the pressure, increase the temperature, and at just the height of that squishing, you inject air, and basically allows for ignition to happen. You don't need a spark, right? It's just that pressure. The other example I have here is what's known as a fire syringe. This is just another example where you show that if you increase the pressure, you're increasing the temperature. And so in that sort of cylinder here too, or like a syringe, there's just this tiny little piece of like cotton or some kind of like tinder, basically. There's nothing else in there but that and some air, and you have this sort of syringe or this plunger that you can push down on. And if you push down on it really quick, then you greatly increase the temperature in a very short period of time, enough that that little piece of cotton will ignite. General physical property where if you compress something, you're generally adding energy to it, and then adding energy increases the temperature. So this is why, or it's thought at least, why a lot of the moons of Jupiter, the ones that are closer and closer, have a lot of internal energy because they're being constantly kneaded by the planet Jupiter as it orbits around. Let's talk a little about Europa. Right, Europa is the next innermost planet, mostly rocky, but its surface is covered with what seems to be a thick ice sheet, like 1 kilometer to 20 kilometers thick. Think that there's probably liquid oceans underneath that ice sheet. And as you can see from the surface, we don't really see any craters, right? And that's generally an indication that the surface is changing often, it's being reformed often, right? Because impacts happen, and so all the planets experience craters or half craters at some point, at least that have surfaces. And so when you don't see them, that's generally an indication that there's movement, there's things that are happening on the surface to reform it. And the up-close picture here is the surface. You see the ice sheet, and it's actually thought that these are, developed by the ice when cracks start to happen in the ice, and there's not really anything they're held onto below, so they can kind of start to move next to each other, and so you start to form these big long lines. And it happens many different times in many different ways, and so you get this pattern, crisscross, and like network of lines and such. Yeah, similar patterns to actually we see with ice sheets and icebergs that float in Earth's ocean. Very interesting, though, having that liquid ocean underneath the ice sheet and the fact that it's being internally heated by Jupiter. It seems like there's probably heat coming out from the very interior, from the very rocky interior, and leading to, well, I mean, having to get out through that liquid at some point. And so we think there's probably what we call hydrothermal vents in that ocean underneath the ice on Europa, which is kind of exciting because on Earth we have hydrothermal vents in the ocean, and there are life forms that have evolved around those vents. And so those life forms are some of the only things on the planet that don't depend on sunlight for their existence. They sort of feed off the energy of those vents and the stuff that comes out of those vents in order to exist. And so on Europa, it seems like there's probably that similar sort of situation, and we think probably a good chance that there actually is life underneath that ice sheet, but living around these hot sort of vents. What kind of life? Microbial life, like single-celled, multi-celled, or possibly even larger? We don't know, but there are definitely plans to try to send probes there and craft that will land and, well, for one, just land at places where it seems like these cracks have happened recently, and so when those cracks happen, water comes up or liquid comes up, and so we might get lucky and find some kind of microbial life in those areas where the liquid has come up recently. The more ambitious plan is to send something there that can actually drill into the ice sheet and go under the ice sheet and find one of these thermal vents and possibly find some life there. Exciting. Io, of the Galilean moons, of the largest moons of Jupiter, this is the closest to Jupiter. Just kind of a cool picture. Io right there, real small compared to Jupiter. And the picture, as it shows here, might be just a little bit deceiving because Io seems very close to Jupiter. It's still 300,000 kilometers from Jupiter in this image. And that's roughly 2.5 times the diameter of Jupiter. So Io is a bit different than the other ones. Jump back real quick. Right, if we look at the relative sort of distances, Callisto is pretty far out, Ganymede's still pretty far out, Europa's a bit closer, Io we're getting pretty close to Jupiter. So going back to thinking about that tidal heating, it depends on the strength of the gravitational pull from Jupiter. So closer in, you're getting a larger gravitational force from Jupiter, you're getting more of that kneading effect. You're adding more heat to that object. So Io turns out to have a lot of internal heat. In fact, kind of like an extreme version of tidal heating. It has an astonishing amount of volcanic activity. Right? All that heat being added to the interior wants to get out, and so it gets out in like volcanoes. They're spewing out molten material from the interior. Something like 400 active volcanoes on Io at any given time. Then the images in the upper inset is like a volcano or the caldera, something like that. And then the lower inset image, you can actually see some material being kind of expelled out, erupted from the planet. Sorry, the moon. The things that are coming out is like lava, like we normally think about, like melted rock, silicate. But also there's a decent amount of sulfur, it seems, and that also mixes with oxygen to make sulfur dioxide. The result of that is that you actually will get these sulfur snows. So like sulfur gets shot up from the interior of the planet, and so it cools and still gravitationally pulled to the moon, and so sort of come down as this snow. It would be a very unpleasant snow to be. Sulfur doesn't get along very well with our own chemical makeup. And you can see it has actually a decent amount of coloring. It's like that yellowish, orangish, and that's generally the color of sulfur, yellowish. Last thing, just going to say a little bit about the rings. I mentioned before that all of the outer planets have rings. Even though Saturn's rings are the only ones that are like easily visible, all the other ones do. They're just very faint. They're not made up of as substantial of things, and so they're kind of hard to see. That said, all the rings, they're not solid disks. If you didn't know, it's not a big disk that's orbiting Saturn. It's made up of a bunch of smaller things. Rocky, icy chunks. So anywhere from the size of like dust grains to like the size of basketball to some as big as like the size of a house. Where these rings actually came from is still kind of an open question. The main sort of theories right now are that they're formed by moons that were broken apart in some ways. There's some kind of impact broke apart a moon that, say, like Saturn used to have, and the debris of that didn't clump back together, but ended up just kind of becoming like this stable debris field that's continually orbiting Saturn. And there's some evidence, for each of these theories. Like for the moons one, if we look at some of the moons of some of these planets and look at some of their rings, they seem to be made up of similar materials. So it's like, okay, maybe that ring was a moon that was broken up at some point. The other end of that, or the other sort of idea, is their rings are made up of material that wasn't really able to form a moon. When the planet was forming, there was that extra material coming around, or maybe there was an impact and there was debris, but it wasn't quite able, for one reason or another, to clump together enough to start forming into its own larger body. And so it's still in that fragmented form. Point out that also these rings generally there's multiple rings on each planet. Saturn, you can see in these images, there are sort of distinct rings, right? There's a really big inner one, and there's a gap there, then there's another ring, and there's a little gap, and there's another ring. You can even see really faint separations between these like little thin rings on the inside there. This image is of Jupiter, and it's a sort of composite image where it looked at a couple of different wavelengths of visible light and overlapped them. But you can actually see the ring, and that's partially because the thing that took this was the very recent James Webb Space Telescope, which has incredibly powerful capability. So even in the visible range, we're able to see the rings of Jupiter. So, last couple of things about rings, and then we're going to talk a little bit about some other physical mechanisms that are related to the rings that we're going to probably come back later on. Up here, just another table, some data, numbers about these rings, like the outer radius of these rings. Jupiter, even though it's a very big planet, much larger than Saturn, it doesn't have very large rings, and the outer radius of its largest ring is still smaller than Saturn's largest ring. The left column is in kilometers. The middle one there is in terms of the radius of the planet, like how much larger the outer edge of the ring is than the radius of the planet. So Jupiter is less than twice the outer ring. Saturn, 2.3. Neptune, relative to the planet size, is pretty wide rings, 2.5 times the radius. The masses of those rings, Jupiter, apparently we still don't know all that much about. That's probably why the James Webb Telescope was pointing at it. Might know more soon. Saturn, fairly large mass, but relative to the mass of a planet, still very small. And reflectivity, again, like how much light gets reflected, a lot from Saturn's rings, right? That's why they're so easily visible. This is a measure of like how visible those rings are. Look at Uranus and Neptune, 5%, not very visible. And so one thing I wanted to point out here is that the discovery of the rings of Uranus was not all that long ago. Again, they're very faint in some of these outer planets, so they're very hard to pick up. And the way that they're actually discovered was utilizing a mechanism called occultation. Basically, it's like when one object goes behind another object, you can't see it. So when somebody was observing a star, a distant star behind Uranus, they were watching as that star went behind Uranus. And you would expect, you're not going to be able to see it when it's behind the planet. But on top of that, they also saw that star go a little bit dim in this region that wasn't behind the planet, right? Just next to the planet. So like it goes by and it dimmed a little bit. And then it went behind the planet, you could see it, came by the other way, and it dimmed a little bit again. That is indicating that there's something there that's blocking the light of the star from getting to us. That was the first sort of indication that Uranus had these rings. That process of occultation is actually used in a number of places in astronomy to find planets in other solar systems, to find multi-star systems, how one blocks another. So this idea of like one object blocking the view of another seems really simple and like, duh, of course. It turns out to be a very powerful tool though. The last thing about these rings, it's kind of interesting, and the reason that they end up setting up in the way that they do has to do with something called resonance. So resonance is a property of waves and shows up everywhere. So if you're using like a tuning fork, you ever seen a tuning fork, you hit it on the side and you hear a certain frequency, a certain sound being made. And that sound is a resonant frequency of that tuning fork. So it's oscillating at a particular frequency, which depends on the size of the fork and how dense the material is. And so they're built in such a way that, like, if I hit it, it's like 400 hertz or something, and I hear that exact frequency. That's the resonant frequency of that tuning fork. If you play a flute, right? You have a flute and you hold down certain, or you close certain holes in the flute and you blow into it, you're setting up a wave, a standing wave in that flute, and that's a resonant frequency of that flute because you're closing those particular ones. So you hit a certain note because it's resonating, the cavity is resonating due to the way that the wave has to move through there because you're closing it. Right? You close it a different way, make a different resonant frequency. Resonance also shows up in like radio and in Wi-Fi, where you have like a tiny little antenna in your phone that's trying to pick up an electromagnetic wave from whatever the nearest radio tower is. The little tiny piece of metal in your phone that's the antenna is able to sort of tune in to the waves that are coming in, and the waves are very small, but if you tune it in such a way, you hit a resonance where those waves start to kind of get amplified, right? And so they're large enough where you tune in and you can actually do something with them. Similar thing with like a radio. If you're adjusting the tuner on a radio, you're adjusting to different resonant frequencies. So you go from like 95.3 and you tune it over to 96.1, right? You're setting something up inside of your radio so that it's going to resonate with that frequency that's coming in. The last example of resonance that I'll show you here is a failure of a bridge that happened in Washington years ago. And, you know, if you take any sort of like slightly rigid object and you wave it around, you'll see, if you look closely, that it's like oscillating up and down. It looks like a wave. And any object like that is going to have a resonant frequency, meaning that like there's a certain frequency that if you were to wiggle it around, instead of just kind of wobbling up and down a little bit, it's going to start to wobble up and down a lot. You get this resonance. So that actually happened to a bridge. The wind was pushing it in such a way where it hit the bridge's resonant frequency, and so it does these huge ups and downs instead of just like a little bit of movement like a bridge is supposed to do. It hits resonance and it goes all crazy, and it eventually fell down. Not great. So why is that related to the rings? Well, sort of where the rings end up setting up has to do with a resonance with the planet's gravitational field. So if we go back and you look at that far left image there, there's that gap in Saturn's ring. And it's a gap in that particular area because of Saturn's gravitational field. Anything that was in that gap is going to sort of periodically feel this extra little tug to come inward, or it might get thrust outward a little bit, right? But it's being sort of pushed around this way and that way. The sort of resonance there is such that it pushes it out of that area. And the way that resonance is ends up being in these strips, right? And so you end up with all this material that gathers in these strips because that's how the resonance of that sort of overall system is looking. The last thing I'm going to show you here, which I think is going to be the end of this lecture, is this video where we see resonance happening in one more instance that might hopefully put it together a little bit more, how those ring resonant thing happens. You might have seen something like this before, but if you put a very light material, like a sand or even like a rice or something, on a metal sheet, right? And then you rub the metal sheet with like a bow, or you can just oscillate it with something, because rubbing it with a bow really is just kind of ends up oscillating the edge of it like quite quickly, and then the whole thing ends up oscillating. And what happens is you get waves on that surface, or the whole surface is oscillating in such a way that there's like wave patterns going on. You don't generally see them, but if you put that really light sort of material on there, then that material is going to be bounced around by the movement of the surface until it gets to like a low point in the wave, right? It gets to sort of this resonant area that's just not moving. And so relative to all the other stuff, there's movement happening, but there's sort of these lines in the areas that aren't moving. And you end up with this structure that's due to the resonance and the resonance structure of that metal and the way that you're vibrating it. So by vibrating that plate, he's using like a violin bow. By vibrating that, he's setting up these resonant patterns on the surface, and all the sand just collects in the places where there's no movement going on. It turns out that those are very much related to the places he has his fingers pressed there. But in the ring structure around a planet, that has to do with the gravitational field of that planet. And so these sort of non-moving places is sort of like where the rings end up being around the planet. That's maybe more about physics, or a little bit more into physics, about resonance. But it's a thing that all waves do, and waves are everywhere in the universe, and so I'm pretty sure that we're going to want to come back to it. So it's going to be helpful if we understand a little bit about resonances for later on. Same thing with occultation. And that's all I got for this lecture. I will see you at the next one.